Okay, and welcome to today's lesson. This is our final tutorial. We are going to continue to verify trigonometric identities. We are still in section 6.3. This is our final installment. I'm going to throw a couple more scenarios at you, some strategies that I've given that we have not actually used yet. So I have 3 examples to look at today. Here's our first one. I'm going to choose to work on this left side. I'm going to use my reciprocal identity right here. I'm going to change the secant of alpha into 1 over cosine of alpha and tangent of alpha into sine of alpha over cosine of alpha using the quotient identity. I want to combine these two fractions, and luckily these two fractions have the same denominators, so I can easily do that. They'll both now have, or the single fraction will have a cosine in the denominator, and the numerator will be 1 plus sine of alpha. I need 1 plus sine of alpha over cosine to be equal to cosine over 1 minus sine of alpha. We haven't seen this situation yet, but this is a common situation. This is our conjugate situation. A conjugate is when you change the middle sign. 1 plus sine of alpha doesn't really help us. I wish that there was some sort of Pythagorean that I could substitute, but I don't have that Pythagorean yet. What I'm going to do is I'm going to multiply this 1 plus sine times 1 minus sine. That's what the conjugate is called. All you're doing is changing the middle, the minus to a plus or the plus to a minus. Make sure you do that to the top and the bottom, the numerator and the denominator, and let's see what happens. The whole point of doing this is so that we can FOIL these together. So there's no reason to leave these in factored form right now. So I'm going to FOIL these. The 1 times 1 gives me the 1. The outer terms are positive sign. The inner terms are negative sign. So those cancel away. My last terms are negative sine squared. When you multiply by the conjugate, you get a Pythagorean identity. I'm going to leave the denominator in factored form. You're going to see why, hopefully soon. This 1 minus sine squared, now I can replace that with the Pythagorean because that's equal to cosine squared. And now you see why I left the denominator in factored form, because one of these factors of cosine, I've got one factor of cosine in the denominator, can cancel out with one of the 2 factors of cosine in the numerator. There are 2 because it's cosine squared, but now there's going to be 1 because I canceled 1 away, and I'm left with 1 factor of cosine in the numerator and 1 minus sine in the denominator. No need for the parentheses now since it's all by itself. And that's what we needed to do. This is the conjugate path. And conjugate can be very helpful, or will be very helpful, to give you a Pythagorean. We don't have anything squared yet, so we multiply by the conjugate so that we have a Pythagorean, and therefore we can substitute more and usually cancel out a common factor. So that's why I showed you this one. Here's B. We're looking at both sides, trying to figure out which side to work on. Which looks more complicated to you? Does an odd exponent look more complicated, or do these parentheses look more complicated? Well, I'm actually going to show you 2 different ways, and I'm going to work from each side. I'm going to start from the right side. I think that that is actually a little bit more complicated. Now, somebody must have taken out a GCF, or actually a CF, I guess. They factored out a sine, but for some reason they left other stuff. There's actually more that I can factor away. This is 4 factors of cosine. This is 6 factors of cosine. So I can still take out another 4 factors of cosine. And that's what I'm going to do. I'm going to factor more out of these parentheses. I don't know why they also factored out to the right side of the parentheses, but I'll go ahead and keep doing that. The cosine to the 4th, I'm going to take out. The sine's already been taken out, so I'll leave that there. If I divide cosine to the fourth out of the parentheses, this term would turn into a 1. The minus sign, of course, is still a minus sign. Cosine to the sixth, if I take 4 of the factors away, I'm still left with 2 of them inside the parentheses. So now I'm sitting at that. And you might see where we're going now. Inside the parentheses now, this 1 minus cosine squared, that turns into sine squared. And now I've got sine squared times cosine to the fourth times sine. I take a quick look at where it's supposed to become, and it's supposed to be sine cubed times cosine to the fourth, and now I can see how that happens. I've got sine squared times sine. That indeed makes my sine cubed, and of course the cosine to the fourth. Verified. That's not too bad if you see that. Take out the remainder of your GCF, and then you've got a Pythagorean to deal with. Let's see if we can work this side. The sine cubed, we've never dealt with an odd, so I don't really like the sine cubed. I might break the sine cubed into sine times sine squared. I can do that. Times cosine to the fourth. I could do that. Because then if I've got a sine squared, I can change that using a Pythagorean into 1 minus cosine squared. Sine squared is what's changing into 1 minus cosine squared. Again, keep taking a hint from what it's supposed to look like. For some reason, they left that sign out here, so I'm going to leave the sign, but I am going to distribute this cosine to the fourth back on in. And I've got sine now times cosine to the fourth times 1 is cosine to the fourth, minus cosine to the fourth times cosine squared is cosine to the sixth. And we're very close to being finished, except it does not look identical yet. I need to flip this sign to the other side of these parentheses so that it looks identical to what the other side of the identity looks like. Put the sign here. Seems backwards, but that's what it has to be. Verified. So actually, in this case, it didn't matter which side you worked on. And if now you look at both of these sides, the work is almost identical, just backwards. Okay, we have one last problem to look at, but it's a very interesting problem, and I'm actually going to show you 3 different ways. Please understand it's very important for me to show you as many ways as possible, because if I just show you one way, that might not be the way that you would necessarily have done this. And again, I'm not teaching you the exact way to do this. I'm showing you different situations, and then you've got your arsenal of tools, and you're going to attack them however you see them. As long as you can get to the final answer, you'll be good to go. So in this first one, the first way that I'm going to show you, I'm going to call it the Pythagorean path. Surprise, surprise. It seems like I always go down the Pythagorean path first. Now this is an interesting Pythagorean path, and it depends on how often you look at your flashcards. Cotangent squared. I know that it's equal to something. It's not actually written exactly like that on my flashcard, but I do know that cotangent squared plus 1 is equal to cosecant squared. I see coco in this one, so I remember that. And I know that the plus is on the same side with the t, so that helps me as well. So if I'm solving for cotangent squared, I'd have to subtract 1. So cosecant squared minus 1 is what that's equal to. So I'm going to change this to cosecant squared minus 1. Now you might instantly say, well, I would never have seen that, so this is not a path for me. I understand that. I understand that, but see if you can. Whenever you see something squared, you can most likely use one of your Pythagoreans. I would suggest writing the Pythagorean down, or at least looking at it on your flashcard, and then manipulating the terms however you would need to. So in this case, I've got cosecant squared minus 1. I'm going to factor this. Every Pythagorean can be written as a difference of two perfect squares. I'm going to factor this now into two factors. Since it's a difference of two perfect squares, I know I take the cosecant and the cosecant, the 1 and the 1. One's got a plus, one's got a minus. The denominator still has not changed. You might see now why I factored the numerator, because now I can cancel out a common factor. Cosecant plus 1, whoosh, cosecant plus 1, whoosh, they're the same thing. Don't worry about flipping around a plus sign. Of course, that would always be true. Leaving cosecant minus 1 all by itself. Now again, where are we trying to get to? We're trying to get to something that has signs in it. So now it's probably a good idea to convert out of cosecant and into signs. So let's see what we've got. This is a reciprocal identity. I know that it's equal to 1 over the sign. And this is just 1, but I might put it as 1 over 1 because I'm sure that I'm going to be combining these two fractions together, and I am. So this has a denominator of sign, so this better have a denominator of sign. So I'll multiply that to the numerator and to the denominator. Now both of these fractions have a denominator of sign, so I can combine them into a single fraction. And the numerator is going to be 1 minus sign. And I'm pretty sure that's what I needed. I draw a little arrow and a check mark. There's my Pythagorean path, or at least the first part involved a Pythagorean. Okay, so let's look at this same exact problem. I put it on a different flip chart. And let's attack it a different way. Instead of starting with a Pythagorean, some people might say, they look at this 1 plus cosecant and they realize that we've already done our conjugate in a previous problem. Maybe conjugate would be a good way to go. So let's talk about the conjugate path. Conjugate path says, okay, I'm going to take this 1 plus cosecant and I'm going to multiply it by 1 minus cosecant, because that would be the conjugate. I have to do to the numerator and the denominator. And let's see what happens here. The denominator, the whole point of multiplying by a conjugate is to actually do the FOIL, so I'm going to do that. And hopefully by now you realize that conjugates, the inner and outer terms cancel away. So it's really just multiplying the first terms to 1, multiplying the last terms to negative cosecant squared. The numerator I'm going to leave in factored form. Again, you don't necessarily know why, or when to leave it in factored form, so I always leave it in factored form until I realize that a factor will not cancel. Then I'll go ahead and distribute. But if you distribute too soon, then you might miss that common factor that will cancel away. Okay, so the whole point, if you're going to take a conjugate path, to multiplying by conjugates is to replace this now Pythagorean with something that it's equal to. Now, 1 minus cosecant squared honestly does not ring a bell to me. I know there's a Pythagorean that deals with cosecant squared, so I'm going to actually write that down. I know that cotangent squared plus 1 is equal to cosecant squared. Again, there's my co-co. Now, what is 1 minus cosecant squared going to be equal to? Well, here's my 1. If I subtract the cosecant squared over to it, I would have to subtract the cotangent squared over to this side. If you can manipulate those terms, you see that this is actually going to be equal to negative cotangent squared. Again, I'm leaving the numerator in factored form. I think it's very helpful to either be looking at the identity to be able to manipulate the terms or to write it down off in the margin and maybe actually do it. Subtract the cosecant squared and you'll have 1 minus cosecant squared. At the same time, you'd have to subtract the cotangent squared and then you'd realize that you have negative cotangent squared here. Now that we have that, I can see that I've got cotangent squared, which will divide away with cotangent squared, leaving just the negative 1 in the denominator. So now I've got 1 minus cosecant divided by negative 1. I don't really like the negative in the in the denominator, so let's just go ahead and move it to the numerator. 1 divided by negative 1 is negative 1, and negative cosecant divided by negative 1 is positive cosecant. forgetting my equal signs. I just like the equal signs to keep my steps visible. I don't really like -1 plus cosecant, so I'm going to rewrite that. Just flip around the terms to cosecant minus 1. And then this is exactly where we were in the previous example, where we converted to the reciprocal 1 over the sine and changed this to sine over sine. And then we got our 1 minus sine divided by sine because they have the same denominators. So if you saw that you could have used a conjugate, that's what that path may have looked like. I'm going to show you one last way, because some people are not going to see the Pythagorean path, they're not going to see the conjugate path, and then what are they going to do? Well, the only other path really is the sine-cosine path. When all else fails, try converting everything to sines and cosines, and let's see what happens. So cotangent squared could become cosine squared over sine squared divided by 1 plus cosecant is 1 over sine. So yes, we get an ugly complex fraction. Complex fraction is one big fraction that has tinier fractions in it. That's okay, we can handle it. What we like to do is get the numerator to become one fraction, which it already is actually, and the denominator to become one fraction, which it's not yet. So I'm going to put this over 1, and I'm going to give the common denominator that needs to be. So I'm going to multiply by sine over sine. So here's my big fraction that has cosine squared divided by sine squared. And in the denominator, now I have the same denominator in that denominator, which is sine, and the numerator is sine plus 1. Okay. So this is a better looking complex fraction because now it's a single fraction divided by a single fraction. When I've got a division of fractions, I multiply by the reciprocal. So cosine squared divided by sine squared, the numerator's fraction is now going to be multiplied by the reciprocal of this denominator. So the sine is now in the numerator, and the sine plus 1 is in the denominator. Usually when you change from a complex fraction to the multiplication, usually a factor will cancel away, and that's true. There's a factor of sine, and there's 2 factors of sine in the denominator, so one of them will go away. And now I'm down to cosine squared is the only thing left in the numerator. The denominator is sine and sine plus 1. I'm going to leave them in factored form for right now. I'm leaving it in factored form because I noticed that in the denominator I have a sine. And again, always keep your eyes on the prize here. In the denominator of my answer, I have to have a sine. So since I already have that, I'm going to leave that alone. But that also must mean that this sine plus 1 has to cancel away somehow. And if this is going to cancel away, then there must be a factor up here that's going to cancel away with it. I don't see that yet, but I will in a minute. I'm going to come over here for more space. Cosine squared, actually cosine doesn't have any business being in this problem because it's all supposed to be sines. So I might change this cosine squared to sines, and the only way to do that is using that Pythagorean. Cosine squared is equal to 1 minus sine squared. And then the denominator, again, I'm leaving it in factored form. You might see what's going to happen now. That 1 minus sine squared up in the numerator now is a difference of 2 perfect squares. And now I can see the factors, and I bet one of them is going to cancel with this one. So 1 minus sine squared is a difference of 2 perfect squares. It factors into 1 plus sine times 1 minus sine, as every difference of 2 perfect squares would do. 1 positive, 1 negative in the square roots. And then you can see the common factor that will go away. Sine plus 1, sine plus 1. They cancel away, and we are left with our final answer. 1 minus sine divided by sine. And that's exactly what we needed verified. So the sine cosine path, might look a little bit longer, but you'll get there. As long as you see something to do and you can get one side to look like the other side, then you have verified your identity. Please do not make any grand leaps. I need to see each step. We all know what the answer is going to be because it's on the other side of the equal sign. So I need to see each step along the way. If you think that it's something that I won't be able to understand, then use a couple more steps to show me. Okay, this is a formal proof of how to do these. Okay, we're going to practice this for the final time in class next class, and I'll see you then, and we'll finish any questions that we have. Thanks for watching. See ya.